Thank you for downloading this episode of In Our Time. For more details about In Our Time and for our terms of use, please go to bbc.co.uk/radio4. I hope you enjoy the programme. Hello. In 1905, a 26-year-old technical assistant at the Patent Office in Bern in Switzerland submitted 4 papers to a German scientific journal. His name was Albert Einstein, and the first of these papers later won him a Nobel Prize. The second provided the first proof of the existence of atoms. The fourth brought into being the famous equation E equals mc squared. But the third paper Einstein published in 1905 was perhaps the most significant of all. It gave the first outline of Einstein's theory of relativity, and it's no exaggeration to say that it was one of the great revolutions of science. In fact, there are 2 theories of relativity, special and general, separated by just over a decade. Together, they offer a new theoretical framework for the nature of space, time, energy and gravity, one of the most important, if complex, contributions to 20th century science. Quote, "Everybody knows that Einstein did something astonishing," wrote Bertrand Russell, "but very few people know exactly what it is that he did." With me to discuss Einstein's theories of relativity are 3 people who do know. Ruth Gregory, Professor of Mathematics and Physics at the University of Durham; Lord Rees, Martin Rees, the Emeritus Professor of Cosmology and Astrophysics at Cambridge and Astronomer Royal; and Sir Roger Penrose, Emeritus Rouse Ball Professor of Mathematics at the University of Oxford. Ruth Gregory, would you begin by giving us an explanation of the scope of these 2 theories of relativity?
Well, I think the sort of impact, or Einstein's legacy really, if you like, with both theories of relativity is to change the way that we think of ourselves within the universe. So it's changed our notions of space and time. I think you may have already mentioned this concept of space-time, that they're both different aspects of the same thing. And it's also changed the way that we perceive, well, in a theoretical sense, I suppose, the way we perceive the world around us. So we have our own everyday perceptions of space and our own everyday perception of time. And I suppose relativity has kind of muddled all these up and said it's all one and the same, and that sometimes our perceptions can be extremely dependent on our point of view.
What did he, let's talk a bit in these terms, please excuse me for being so vernacular, but what did he overthrow? Let's just take Newton. There was Newton's world, and before that Galileo. Let's take Newton's world. What did he overthrow that was set in Newton's world and people thought set forever in Newton's world?
Well, perhaps overthrow is a strong word, but I think the obvious thing that would come to mind there is this notion of absolute time, which we often associate with the ideas of Newton's laws, that there's a sort of cosmic clock that goes on ticking, and that everybody would agree upon what time they were at, and the rate at which the clock ticks. This actually does pervade our own sort of notion of common sense, because quite often, certainly, say if you watch Star Trek or the usual science fiction programs, there is this idea that there's sort of a definite order of things, and that's really not that true, and sometimes it can actually be false. So I think it's this notion of absolute time that's probably the biggest single thing that changed as a result of our new understanding of space-time.
And Newton's idea of the universe being a great master clock, with a clockmaker.
Yes, and I think it's become far more. I mean, if you say subjective, it can possibly sound unscientific, but actually it can be made scientific. I suppose relative, perhaps, is another way.
Martin Rees, the theory of special relativity is based on 2 basic ideas, the first of which is the principle. Would you explain the principle of relativity to us?
Well, as Ruth said, the original idea was that there was a sort of absolute time ticking away, and also an absolute space, what people call the ether. And one thing that Einstein realised was that neither of those statements were true, and if you were in a lab making measurements, etc., those would be just the same if you were in a lab moving at a big steady speed with respect to the first one. So, in effect, although his theory is called relativity, what's important about it is some things are invariant. depending on how you're moving. And that's one point he did. But if we think of what he did beyond what Newton did, Newton gave us a very good theory of gravity, about how the planets move, etc. And Einstein didn't really overthrow Newton. He transcended Newton, I would say, in two ways. First, his theory applies even when gravity is very strong. It applies when things are moving very fast, in a way that Newton's theory didn't. And it also applies when things are moving close to the speed of light. And he gives a much deeper insight into why Newton's theory works. Newton found that all objects fall at the same speed. He didn't know why that happened. Whereas in Einstein's way of looking at things, it's completely natural that everything should fall at the same speed. He gives much deeper insight.
So the two basic things are the speed of light and the idea of basic physics, isn't it?
Yes. Well, I mean, going back to the speed of light, there was a famous experiment called the Michelson-Morley experiment that was done in the late 19th century, which surprised everyone, which had showed that the speed of light was the same depending on however you're moving. And this is quite different from any other speed. If you move towards a source, you'd expect that the relative speed would be higher. Away, it'd be lower. But that's not the case of light. And that was a mysterious thing which was explained by Newton's theory, because if you moved, your clock rate changed as well. There's a big debate about the extent to which Einstein was influenced by the Michelson-Morley experiment. He thought he knew about it. But the thing about Einstein is he seemed to come to his ideas through sort of deep thought, rather than necessarily trying to explain some physical anomaly.
There's also the Maxwell, isn't there? Maxwell's four equations.
Well, that's right.
1873.
Yes. Well, Maxwell was the first person who related electricity and magnetism, and the most important consequence, in a way, of Maxwell's theory was he realized that light waves, and indeed radio waves as well, are waves propagating in empty space of electric and magnetic forces. And when Einstein looked at Maxwell's equations, he showed that they could be easily understood in his theory in a more complete way. So he, in effect, completed Maxwell's theory, and he, in fact, always said that Maxwell was the only other of his predecessors on the same level as Newton.
So interesting remark you made on the way through there, Martin. You were talking about it was to do with thought rather than what. What's the distinction you're making there?
Well, he famously did thought experiments. He asked what would happen if you were riding on a light beam, for instance. And he realised that led to paradoxes, and that's what led him to his theory. And then, in his later theory of general relativity, he said, what would it be like if you were sitting in a freely falling elevator? And he realised that if you were in that situation, you would just think you were in empty space, you wouldn't know about gravity. So he came up with these sort of thought experiments, which led him to his deep insights, and he was guided by them as much as by trying to explain any puzzling phenomenon.
So this is the first of two theories, the theory of special relativity, which was in that Annus Mirabilis 1905, yes. And there were these four papers produced by this young man working in a patent office.
That's right, and of course what is amazing is that these four papers did all come from one person who was an unknown 26-year-old, and then it was 10 years later that he generalised his theory to account for the case when things were not just in uniform motion but were influenced by gravity, and he had an entirely new insight into what gravity was by showing that it implied that space was not always uniform and flat. If you were near a big object, space was curved. Now that's a technical term. What that means really is that if you tried to draw a triangle, then the angles wouldn't add up to 180 degrees, just like if you draw a big triangle on the surface of the Earth. The angles don't add up to 180 degrees because the Earth's surface is curved, and even if you try to do this in space, then if you are near an object that has a gravitational field, then the space is curved in that sense, and that was his unique insight into what was actually happening when something is seemingly affected by a gravitational force.
Roger Penrose, can you speak more about this special relativity and how he came to it and how he developed it?
Perhaps I should first mention that the idea of relativity, although Einstein didn't terribly much like the word, I think he regretted it later. But
why did he regret it?
I think it suggests that it's all the physics, if you like, is just a question of how you think about it, and different people might have different views, and it doesn't matter. That he really had a view that there was an absolute world out there, and that what's relative, if you like, is the notion of time and the notion of space, and these things are relative to a particular observer or measuring system, but that the physics as a whole has an objective reality external to ourselves. And I think the feeling was that it was all relative, and you could think what you like, in a sense. Where certain notions are relative. I think this...
So relativity gets in the way of a theory, in a way? You think?
In a way,
I
think that's true, yeah. Yes. Well, you see, Galileo had a very good idea of relativity in the same sense that, I mean, he needed it in order to get people to accept the idea that the Earth was in motion around the sun. You see, well, why didn't you feel it? Why didn't things go swishing with the terrible winds and so on? And he explained very nicely about people in a boat, and if the boat is travelling at a uniform speed, and there would be drops of water going down, and they'd hit the little basin underneath, no matter how the boat was moving. And a nice thing about flies in a container, and they would all be, you might imagine they'd all be trapped at the back, you see, whereas he said no, they fly around perfectly happily. So he had this appreciation that uniform motion, something in uniform motion, you wouldn't be able to detect that motion by means of experiments that you did internally. And what was revolutionary about Einstein's form of relativity was that the speed of light had to be the same speed, however you move. Now that would be all right if light was...
And in whatever direction it went.
Yeah, that's right, whatever direction, whether it's moving in the direction that the boat's going or in the opposite direction. And it didn't make any difference to that speed. That would have shocked Galileo.
Why is that so very important?
Well, mainly because there was a wonderful theory, as Martin's already said, which explained light, which was Maxwell's theory. Maxwell had this theory which integrated electricity and magnetism, and in doing so, his equations show that you also would have electricity and magnetism sort of self-propagating through space, and that this self-propagation would travel with the same speed that light seemed to go at, and so he postulated that's what light was. And not only did that explain light, but it also explained that light is just one set of frequencies within this whole huge range, and we now have radio waves, X-rays, all sorts of things which people had no idea about before. So that this theory, wonderful theory, that Einstein agreed was a fantastic theory, simply didn't seem to have this relativity principle in it. That is to say, if you were moving with a uniform speed in some direction, according to this theory, you might think the speed of light was different in two directions. So you had to take these equations and realize the impact that taking them seriously had on one's notions of space and time. So you had to, first of all, that if you have a ruler moving at great speed, you have to consider that ruler is shortened in its direction of motion. And the other thing was this time dilation, which means that if you have a clock, and if that clock, relative to your own frame, is moving at great speed, it will seem to run slow with respect to you. Now, these are all things which you wouldn't see how they would all fit together into one scheme, which makes sense. And that's what Einstein was able to show. It actually didn't fully make sense, in my view, until Minkowski came along. You see, people say, well, Einstein introduced this idea of space-time. He didn't. He had just sort of had ways of transforming one thing and another so that it actually hung together and made sense. But it was Minkowski who fitted this all together in a nice geometrical four-dimensional picture and said it's just, apart from one little detail, it's just like Euclidean geometry in 4 dimensions. And Einstein at first was rather horrified by this. He thought that's not the way to... And then he realized later that is the way to look at it. So that the four-dimensional picture, which is a wonderful way of seeing how it all fits together in one absolute scheme. So I think this is in a way why the idea of relativity became recognized, at least by Einstein and many others, as not an appropriate term, because the space-time is an absolute thing. It's out there and it's absolute. The way we look at it, we have our ways of measuring time with clocks and rulers and so on, and those things have to transform in this funny way that Einstein recognized. But it's the absolute space-time which is then reinstated as the absolute notion.
And you mentioned time dilation. Could you just explore that a little more?
Yes. Well, the most puzzling thing about it was the thing that's sometimes referred to as the twin paradox. So it tells you that if you travel at great speed, then with respect to somebody who's not travelling at that great speed, the clocks will run more slowly for that person who's running at great speed. So you can imagine a space traveller. They usually talked in terms of two twins or something. I don't quite know where they had to be twins, but never mind. One of them goes off to a distant planet at nearly the speed of light and comes back again, and the other one stays at home. Now, the one who travels out and comes back at a great speed will age much less than the one stays at home. So the one might have aged by 50 years, and the one who's travelled back out and back will maybe only have aged 30 years, you see. And that seems like a paradox. It's not actually a paradox, it's actually what happens. And people have done experiments in aeroplanes even, and all sorts of things, and you can put a very accurate clock in a plane and travels off and comes back again, and you see the clock has not registered as much passage of time as the one which has stayed home on the Earth.
And is this, Ruth Greger, is this one of the ways to test time dilation?
Yeah, so, I mean, well, as Roger was saying, there have been experiments where you take put clocks on a plane. Of course, that's also testing part of general relativity as well, because we also know that if we have, as Martin said, if we're near a large matter source, our space-time curves, and what that does is it affects the passage of time, and so objects, it has the consequence that objects that are near a large body, their clocks move more slowly than objects that are further away, and that is experimentally verified. So we do have this somewhat more elastic notion of space and time, which I think is what sometimes people struggle with when they think about relativity. But as Roger was saying, that it's really this four-dimensional space-time that is somehow the invariant, but it's what's being perceived that tends to change. It's a bit like saying we have a notion of sea level as a particular altitude, but one's notion of where the ground is can change depending whether you're in a mountainous region or somewhere very flat or somewhere by the sea or somewhere far away. So it's really because space is only part of the picture. It's not the full picture. So if you try and split it up into these two different things, you inevitably maybe get different answers depending on how fast you're moving or where you are. And it's a bit hard to kind of get around.
Can you encapsulate space-time for our listeners?
Oh, how to? You mean how to visualize it?
Yeah.
So I think a rather nice way, at least although this is sort of impinging on general relativity, a rather nice way sometimes of thinking about it is visualizing it almost as space. So people often have this notion of rubber sheets, where so a rubber sheet, if it's laid on the top of a table, might be just nice and flat, whereas if you distort the rubber sheet, that's a way of picturing curvature. You're distorting this this simple we say it's a two-dimensional surface because we can move in two directions on it. And so for space-time, we kind of extrapolate, we go beyond this two-dimension, we add two more dimensions, one for another dimension of space, and then our passage through time is an extra dimension again. So I know people are different in terms of what we call spatial awareness. In reality, when we look at the world, each eye is only seeing a two-dimensional image of what we know to be a three-dimensional world around us. But we're quite comfortable in art with looking at two-dimensional images, and our brain makes them look three-dimensional. And we kind of just have to make that extra step by imagining that a passage through time is just somewhat like that extra dimension. It's a little different, true, but sometimes that helps to visualize this additional dimension.
Martin Rees, the final paper Einstein published in 1905 contained the most famous equation E equals mc squared. What does that mean, and how does it complete his theory?
It really tells us that if something is moving very fast, it carries a lot of energy with it, but there is a limit to the amount of energy that any mass could have. And we've learnt from chemistry and from nuclear physics that it is possible to convert some of the mass into energy, but there is a limit. In chemical reactions, it's only about 1 part in a million, but in a nuclear bomb, a much bigger fraction is converted. So he just showed that mass is in effect a form of energy, and this again is showing that things can be converted more readily than people thought before. But I think going back to what Roger was saying about the twin paradox, it does sound a paradox and counterintuitive, but we've got to remember that what we call our intuitions are things we grew up with, which apply to the everyday world. And in the everyday world, of course, Newton's theory is fine, clocks tick all at the same rate. But the reason it's counterintuitive is that the distinctive consequences of Einstein's theory apply only if you move at a big fraction of the speed of light, which of course we never do, although particles do, or if we consider very strong gravity. So it's like in other areas of science, like the micro-world of atoms, that things are counterintuitive, but that simply means they're away from the everyday experience that our brains evolved to cope with.
You said, to pursue something you said earlier about him, about Einstein taking thought, and you also said in the notes that I got that you thought he worked more like an artist than a scientist at one stage. What did you mean by that? Or as much like, not more like?
Well, I think he had an imagination, but I think when people talk about creativity in science and creativity in arts, then there are some similarities but some differences. And the main difference is, of course, is that if you create something in the arts, that's your distinctive achievement. No one else will do it. In most of science, if A doesn't discover something, B fairly quickly will. And that's true even of Einstein. But I think if we look back on the history of 20th century science, Einstein made a more distinctive imprint on the subject than any individual, in that had he not thought of his theory of general relativity in particular, then it might have been quite a long time before that was thought about in the same way. So he was someone who perhaps made a more distinctive imprint on the way in which things were discovered in the 20th century than any other scientist. And so in that sense, he had greater individuality in his achievements. And that's perhaps one of the reasons why he is the unique, iconic figure. I think the other reason for that is that he was famously vindicated in 1919. There was this famous experiment where British astronomers went to observe the position of stars in the sky during an eclipse, and a famous prediction of Einstein's theory was that light would be bent passing close to the sun, and therefore a star would look in a slightly different position in the sky if you looked at it when it was near the sun, which you can do only, of course, during an eclipse. And this experiment was done, and the results were not all that convincing, but fairly convincing. But when this was announced in 1919, there was huge razzmatazz, and that is what made Einstein a famous figure to the public. And, of course, added to the scientific interest was that British scientists had confirmed the work of a German scientist during just after World War I, etc. So it was after 1919 that unique celebrity accrued to Einstein in a way that never did to any of the other great figures of the 20th century, in particular the people who developed quantum theory in the 1920s. They made an equally important conceptual breakthrough in a way, but that was a more collective effort. No single person dominated, and that didn't really strike the public imagination so much.
You earlier, Roger Penrose, you mentioned Minkowski and his mathematics, which completed, in fact, confirmed, really, Einstein's theory. Can you just explain can you tell us something, those of us who don't know about this stuff, what that entailed, what mathematics you're talking about?
Well, it was really the idea of geometry. I mean, Euclid established a very good geometry of three-dimensional space. Once Descartes and people introduced the notion of coordinates, it was not hard to see how you could generalize that to 4 dimensions or any number of dimensions. However, the key difference in what Minkowski did was, well, technically it was just a sign that time and space behave very similarly apart from a minus sign. Now, that's difficult to explain, certainly over the radio, but most of the ideas of Euclidean geometry will carry over. But then people say, well, time and space aren't really the same. And that's right, they aren't the same. But the difference is the subtlety of a plus sign changing into a minus sign. And if you use the same formula, say the Pythagoras theorem, where you say the hypotenuse, the sum of the squares of the two sides is equal to the square on the hypotenuse, that formula will apply in space-time also, but with a minus sign. You have to subtract instead of add them. And this, I mean, it's a technical point, of course, but if you do that, then you can see that the idea of length is then the time measured by a clock. So you have this beautiful 4-dimensional geometry, and instead of thinking of length as you know, what you would measure by a piece of string along a curve or something like that, you think of the world line of a clock. Now you see, a clock or any particle would be represented by a curve in space-time, because that's the history of that particle. And then along that curve, there will be a measure of length, but this is the time as described by the clock. Now you see, the twin paradox is a bit like if you take 2 points in a Euclidean plane and you say, what's the distance between those 2 points? Well, if you put a straight ruler between them, you have a certain length. But if you have a curve, say a piece of string which connects those, that will always be a bit longer. Now in space-time, you see, if you have 2 events, where this is one where the twin goes off in the rocket ship and the other one stays at home, then the one staying at home is you think of that as a straight line, but the one who accelerates, go off and comes back again, that will be a curved line. Now the only difference between that and the Euclidean case, where you say the curved one is longer than the straight one, it's always shorter than the straight one. Now the length is not a length now, but it's the time as measured by the clock along that curve. So you find that the twin paradox is not really a paradox any more than if you measure distances on a plane, and one is a straight distance and the other one's a curved one, there'll be different distances. And likewise, you have the straight path, which is the one by the stay-at-home twin, and the curved path, which is the one who travels, that those distances are not the same. But now it's the shorter one, which is the curved one. And that's a sign. So it's only this plus sign changing into a minus sign thing. But apart from that, it's just like Euclidean geometry, and one can understand relativity just with this little flip of a sign, and it makes a lot of sense.
The special relativity was one of the 2 theories. Yeah. The second one was general relativity, which is harder. What did special Martin? For me, very much harder. Martin, what did special relativity leave out? Why did he want to go on to do the next one, and what did the next one bring?
Yes. Well, special relativity applied just to particles moving in otherwise empty space, but we know that our actual world has objects in it, heavy objects, etc., and he incorporated gravity. Again, his results were more or less duplicating Newton's in the conditions we could observe, and in fact Newton's theory is still good enough to program spacecraft to go to the planets. But the reason why historically Einstein's relativity is so important is we now know that there are places in the universe where Newton's theory is no good at all. In understanding the Big Bang itself, we need to use Einstein's theory, and also there are objects where gravity is so strong that light is bent very drastically, and of course black holes. Black holes are actually the most distinctive and remarkable prediction of Einstein's relativity, the idea that space could be so curved if an object is compact that not even light can escape from the object, and it just leaves, as it were, gravitational imprints frozen in the space around it. And these were predicted by Einstein's theory, but only discovered by astronomers in the 70s and onwards. And it's rather interesting, actually, that Einstein, although he pioneered his theory, in his later life he didn't have huge interest in what seemed to us now to be its most important consequences. He was never particularly interested in black holes, even though he spent his last years working at Princeton, where Robert Oppenheimer had done pioneering work on black holes in the late 1930s, and he never really saw this as so important. And the other arena where his theory is important, of course, was cosmology. And back in 1917, he tried to apply his theory to a universe. He thought that the universe was some sort of finite closed system. And he realized that he had to insert an extra force into his equations for this to work, because if he just took his equations as he'd worked out in 1915 to this universe, and it was static, then it would start collapsing. And he thought then the universe was static. But it was discovered about 10 years later that the universe is expanding. And he then was persuaded, in fact by other people, mainly by a Russian called Friedman, that his equations, without putting this extra force, could very neatly account for an expanding universe. And that's one of the most important consequences, of course. But what happened later was rather ironic, because one of the big discoveries in cosmology just over 10 years ago was that distant galaxies are not only expanding away from us, but they're accelerating away from us. So there really is this extra force which is pushing things apart. And that's actually the same extra force which Einstein put into his theory in 1917 for the wrong reason. He wanted to stop the static universe collapsing, whereas we now know that force is there, and it's there to everyone's surprise, and it's actually causing the universe to accelerate.
Ruth Gregory, can we talk about the explanation of gravity?
Yes, well, I mean,
in general relativity.
I mean, I have to say it is, you know, even looking back, quite a remarkable achievement, you know, that Einstein decided his theory was incomplete and persistently looked to
the first theory of
special relativity, because it didn't really take into account sort of acceleration and also this notion that we you know, near large massive bodies, we also tend to accelerate. And so he sort of went away, he learned mathematics, which he always famously said he found it very difficult, so we shouldn't feel too bad about finding it difficult, and came up with actually an extremely mathematical theory of gravity, where we replace this notion of a force by simply saying this space-time that we've been talking about is curved. And so, going back to the rubber sheet analogy, if we put something very heavy, cannonball, on a rubber sheet and distort it, if we try and then roll a little marble around, and I don't know, you may have seen these in science museums, this marble is not going to go in a straight line. It's going to sort of curve, or sometimes even orbit like the Earth orbits the Sun. So general relativity took something that I think already is quite conceptually bizarre for everyday, you know, our everyday experience, and then said, oh no, it's even more strange. You know, it bends, it distorts.
Martin, come in.
Yes. Einstein's real belief all through his life was that geometry was at the basis of reality, and that's what led him to his idea that you could think of gravity by thinking of more complicated geometry. And of course that remained his belief all through his life, and in fact in the later part of his life he tried to have a more general theory which incorporated electric forces and magnetic forces in the same way, by bringing in extra dimensions, things more complicated. This was his attempt at a so-called unified theory, and this was in fact doomed to failure, as we can now see, because we realise that there are other forces involved in atomic nuclei he didn't know about, and so it was clear his view was destined to fail. But he had this rather noble effort to try and see if he could geometrise all of nature, and of course that's something people are trying to do now with string theory in a more complicated way. But that was always his belief, that there must be some underlying geometrical way of looking at the whole of nature.
Roger Penrose, we have a phenomenon called gravitational lensing in general relativity. How important is that, and could you explain it?
Well, that was an effect which Einstein appreciated. Well, it goes back to the experiment, in fact, that Martin referred to, that the British astronomers Eddington confirmed.
In Patagonia, wasn't it? Anyway,
no, that was off the coast of Africa. This was. But the gravity also bends light. You see, this was a deduction that Einstein made first of all from his general principles of relativity, that light ought to bend under gravity. And he initially, people went to, I think it was into Crimea, they were going to do an experiment. But fortunately, they weren't able to do that because Einstein had the answer wrong by a factor of 2. And by the time the experiment that actually was performed by the British astronomers, he had it right, so that when the observation of the bending of light was confirmed, it was actually in accordance with Einstein's predictions. But that was a bit of good luck in a sense. But the thing is that since light bends, it also, you could imagine a situation where you have, say, a massive body relatively nearby, and a long way off something else. Now, the massive body, the intermediate body, will act as a lens, and it will cause the light to be focused sometimes. So you see images of the much more distant objects spread out. And there's a particular example which Einstein introduced where it would actually, you'd see it as a ring. So rather than just seeing the distant object magnified, because the lens isn't a very good lens, if you like, it actually gets stretched into a ring. And things like this have now been observed. I think Einstein thought you'd never ever see such a thing, but observations have got so fantastic now, and so many different, you can look at galaxies all over the place, you see, and every now and again you spot one where there is another much more distant galaxy, and the distortions that the lensing effect has on those very distant objects can actually be seen. And this is one of the most remarkable achievements of general relativity, because it allows one to tell when there is mass out there, even if you can't see it. So there is this dark matter, for example, which people argue about whether it's really there or not. But one of the most convincing pieces of evidence that it really is there is you can see the lensing effects due to this dark matter on much more distant galaxies.
Ruth, you wanted to come in.
Oh, no, I think it was just, I was more or less agreeing with Roger there. I think it actually highlights also, when you were asking about general relativity before, in many cases in theoretical physics, we're often driven by experiment, trying to sort of explain an anomaly or something curious, whereas with general relativity, it was the theory that came before any experimental facts, and apart from the odd thing like light bending or the way Mercury moves very close to the sun, we somehow felt, or Einstein felt, and the theoretical physics community felt, that this was a theory which was not really going to have practical applications, or apart from almost philosophical questions like the start of the universe may not come in.
Sorry, Martin and then
yes.
Roger.
Well, it's true that the evidence for things like gravitational lensing and black holes didn't really come in until after the 1960s, in Einstein's last decade of life. And that is why relativity was something of a sort of scientific backwater between the 20s and the 60s. And that's part of the reason why Einstein became a rather isolated figure. Most of the younger scientists were working on quantum theory and things like that, and it was only much later that we realized that the implications of Einstein's theory are very important in the universe.
Roger.
Well, 2 points. First of all, when Ruth says practical, you see, usually people don't think of, maybe astronomy or cosmology isn't very practical. But in fact, the general theory of relativity is a key part of the GPS system, so the global positioning systems that we use in our cars and to get from A to B, and they depend on the time dilation effects, which are part of the absolutely crucial, not just to special relativity, but to general relativity, and they just wouldn't work without general relativity. So we do actually have practical applications. The other point, I think, just going back to a point that Martin was making about science and people, they might make, if it's person X hadn't made a discovery, then person Y will make it just perhaps a little later. I think that was very true of special relativity. In fact, there were a lot of other people who more or less had it. Poincaré, Lorentz practically, and certainly Minkowski, he might well have had the ideas without Einstein. But general relativity, I think, is a different kettle of fish. It's a completely different set of ways of thinking about physics than other people had at the time. Of course, maybe somebody would have eventually had this idea, but it's one of those ideas which it might, even now, I suspect, might not have come about if it hadn't been for Einstein.
Fundamental shift.
And how long did it take for other physicists to recognise this?
I think they recognised or accepted it as a theory pretty much straight away. What I think took a lot longer was to actually believe that it had anything important to say or anything relevant and practical, just as Roger picked up with the GPS. I think acceptance.
And to test it precisely, because
the
effects are very small in a solar system.
Yeah.
So we needed to have more distant objects to test it precisely, and that only became possible more recently.
Yeah.
Is it still centrally relevant to the way you people are working at the moment?
It is the way I'm working. I don't know.
That's
why we're here.
Completely. It completely underpins our notion of cosmology. So there's been a big splash over the results from the Planck satellite, which gave its first data release just over a month ago, and absolutely underpinning everything they're doing is Einstein's theory of gravity with his famous cosmological constant that Martin was talking about earlier. That is their absolute sort of baseline, fundamental, core truth, if you like, in the way they've analysed their data. So it is completely underpinning a whole range of different areas.
It's back in the centre of theoretical physics.
Yes.
Well, thank you all very much for that. I think I learnt a lot. I hope I can remember a lot, but thank you very much for making it so clear. Thanks to Ruth Gregory, Martin Rees and Roger Penrose. Next week we'll be talking about prophets and the nature of prophecy. Thanks for listening.
There are many more Radio 4 arts and discussion programmes to download for free. Find these on the website at bbc.co.uk/Radio 4.